Who's used React too? Okay, well, for the rest of you, okay, we got this. How many people here identify as Python developers and programmers? Okay, cool. How many identify with JavaScript and TypeScript? I don't know what the heck the rest of you are doing. We got product managers? Okay, all right. No shade. It's a hard job. It's thankless. All right, so I'm Rachel Nabors. I've worked with the standards that power today's web with Mozilla on Firefox's dev tools, the W3C on web standards, and Microsoft's Edge browser, and even on every front-end developer's favorite, React. I've spent the past 3 years consulting with AI startups and LLM/big browser companies you may have heard of in the Bay Area on all things web, AI, and UI. And recently, I've become the principal developer experience engineer at Arize. Have you or your CTO ever had a situation where you've ruined an agentic flow with a slight change of a prompt, or maybe you tried to upgrade to a different LLM and suddenly things are broken and there's a sev and you're getting called in the middle of the night? You can put your hand up. It's all right. There's no shame here. Yeah. Have you ever been the person responsible for that? That's all right. You don't need to shame yourself. I see some smiles. I know who you are. Anyway, so you need observability, and Arize offers one for models and the agents who love them. And today I'm here to talk about how AI is costing you. Every time you reach for a foundation model like GPT-5 or Claude, it's costing you, your users, the environment. I'm curious, how many of you are using a big frontier model in production today? Sweet. Okay. Well, I guess you came to the right talk. Let's look at some of the costs of one-size-fits-all inference, as it were. There's security costs. When you send data to remote servers, you always carry the risk of exposure, interception, and retention by third parties. We have cases where use from remote AI chatbots actually led to sensitive business data being stored, breached, or leaked. This is a common occurrence. Latency costs user experience. We've got research on mitigating response delays on LLMs in chats in VR, and found that user patience is around the 4-second mark today, but it's always coming down. So that means tomorrow it's probably closer to 3 seconds, and in a year it'll be 2 seconds. It costs your business. Third-party inference costs are uncontrollable compared to API costs. Agents eat compounding levels of inference. The more you ask them to do, the more they're going to eat, the more it costs you. And of course, if you aren't connected, it doesn't work. For instance, maybe you are trying to support people who do not have connectivity to outside systems, perhaps without Wi-Fi, perhaps they're in a mine, or perhaps Claude's just having a bad day and the network ditched you. Now suddenly, their outage is your outage. All right. Now, we've heard that token costs are falling. That's great. But unfortunately, total inference spend is rising because, once again, agents and reasoning workloads consume tokens faster than the prices drop. But fortunately, we can completely eliminate all of those costs. And it starts by asking ourselves, do we really need an LLM for this? Now, we can use task-specific models that are small in size and power compared to a foundation model. A good cheat sheet I use is a camera pointing at something. You can use a vision model like MobileNet or MediaPipe. You do not have to use Gemma in its multimodal capabilities just because there's an image in there. If a microphone is recording, you can use a small model like Whisper or Wave2Vec. And, if you're using chat, translation analysis, you can use a small language model like Gemma or Qwen. But that's the interesting there. Those small language models, those are called LLMs. For times when we don't need the language power of a full LLM, a large language model, we want the power of a generative pre-trained transformer, but we don't need the sum total of human knowledge in a black box. When you are translating customer reviews, do you really need to know the intricacies of multiple world wars and physics computations? Probably not. You just need to know which word should follow this word. Now, SLMs, they contain millions and billions of parameters. So LLMs, on the other hand, they contain billions to trillions of parameters. So if this dot was one of this mint dot up there was one of their smaller LLMs on market, this little green dot here represents the footprint of one of the larger SLMs that's on the market here. It's an order of several magnitudes difference. I like to use the visual because we throw around billions, trillions. What does that look like? Someone draw a dot on a screen for me. Anyway, additionally, SLMs consume way less energy than LLMs to produce similar responses. Now, this is most SLMs, they fit into the space of, a billion parameters. That's like 2 gigabytes in FP16. SLMs for mobile and web are deployed with quantization, 8-bit and 4-bit, which can have recorder, disk, and memory requirements. So think of this grid as like an upper bound estimates. They're so light that they can be put on devices. My Pixel has a little tiny model on it that hopefully handles lots of things and makes it very warm on a hot day. Can't get enough of those TPUs. They cannot come soon enough. Now, small language models all are production ready. Let's see. NVIDIA said that SLMs are the future of agentic AI because they're very good at taking orders and spitting out content without thinking too hard. And to help you visualize how much less energy that they consume compared to an LLM, I made this handy chart here. And of course, task-specific models come in even lower. So if you need to use visual, but you don't need, for instance, to translate an image into words, a task-specific model is definitely your bestie on that one. All right, so the benefits. More secure, works offline, no fees, more efficient, lower latency. It's so useful. I've been using a local AI for some time. This is Goose. It's an open source harness and GUI. And with it, you can just add Gemma. And it's pretty much able to answer questions for me, often as well as Claude does. One of my favorite benchmarks is to ask a model, how likely is it that ichthyosaurs had echolocation? They look like dolphins. They're marine reptiles. They're extinct. But you can see just how much knowledge a model has absorbed by whether or not it's able to reason about the likelihood that an ichthyosaur had echolocation. There aren't a lot of papers about it. So how do you pick the best model for the job? I built a little framework for Google when I was writing for web.dev that I use on my own products. I nicknamed it Prototype Big, Deploy Small. Yes, that's me. Let's make it a thing. I'm going to see how many catchphrases I can create in this talk because I feel like Anthropic just ends up stealing them all. Like skills, come on. It's just markdown files in a folder. I've been doing that for ages. How dare you brand this? This is just common convention. So we're going to see if we can do some branding here. Anyway, prototype your system with a foundational model to prove that it can work, but then convert parts of that system to smaller models and specialized models for production. That's basically what this boils down to. And it starts with step 1, just proving it's possible. You want to test whether what you're trying to accomplish is possible at all by using the largest possible model. Now, for most of us who just started by building with the largest model, this is a piece of cake. We've already got step 1 done. But you could use a foundational model like Gemini or a task-specific model, but you're probably just going to go for a big one. This is actually from my app that I built called Mima. Mima is the browser of the future for teenage girls. This feature summarizes, this feature that I've created, it summarizes when a thread has more than one reply in it. And originally, I built Mima, and I was just like, give it a Claude API key. Unfortunately, teenage girls don't have Claude API keys, so that was where I went wrong. They also don't use desktop apps, but transitioning from an Electron app to perhaps React Native, that's for a different talk, not this audience. But anyway, here we go. Your first mistake was an API key was required. All right. Now, step 2, collect a set of inputs and outputs that you want to use as success. Phrases in one language and their successful translations into another, for instance. Or in this case, I made a golden data set, a set of meticulously curated, high-quality, human-labeled input-output pairs. used as the ground truth to validate and evaluate how my model's doing. I basically exported a collection of public conversations that I had had that Claude had summarized very well. I was like, yes, Claude, good job, Pat. This was totally worth the 44 cents I spent on inference to generate all of these. So this is what that looks like. It's a JSON-L. You would have this as JSON-L, not JSON format, but I've laid it out here. Got the author handle, their display name. This is all the inputs. The data that we're using is curated from my own conversations, and all of the outputs were generated by Claude. Now, there were 14 threads, each evaluated for summaries and for annotations that should appear in the model. Because there's two ways that we make in Mima that we share. We use AI to summarize. There's the summary that you see when you're first using it. Actually, hang on a minute. Did I have that in my video? I didn't realize it was actually a video. I was like, what's going on here? Anyway, got the API key, cross out. There you go. So as you can see, does this have a little, hang on. No, it does not. All right, anyway, you can see that some of them have summaries. And that's when they have more than one comment. So more than one comment, you get a little summary saying what's happened in there. And if it's just one comment, you'll just see the comment there. Ta-da. So it gives you a nice little summary of what the person said. Phew. Boop, boop, boop. So yeah, the golden data set includes the inputs, the whole list of threads, the outputs, what the cute little summary should say, as well as some annotations, as there is an overview mode that kind of links to where things were said in much longer paths. So 14 of those times 2. Next, defining success. These are the things that we'd be measuring in the experiment. 1, is it outputting valid JSON? If it's not valid JSON, I can't use it, so it might break the system. Structural validity for the references, making sure that they point to actual messages that exist, not hallucinated. Factual consistency. This is the only one that actually requires an LLM. You can't just, figure it out using code. This is the expensive part to test, because I need to go to another language model and say, hey, yo, can you look at this thread here and tell me if it is, this summary actually represents what's in the thread correctly? That's a big leap of trust. But then length compliance, does it stay within 90 to 100 characters? And then, of course, P50 and P95 latency being your medium weight and your worst case scenario. Now that you have the set of inputs and outputs, it's time to get to test them. Woo! So first off, I chose to use Phoenix. It's open source. It's free. Anybody here use Phoenix? Thank you. I see you back there. Anyway, it also happens to be worked on by the team at Arize, so I had access to all of the engineers. I actually didn't need the engineers because the Phoenix skills are pretty good. I just popped them into my workflow, and I was like, all right, guys, we're going to be building with this. And we took off from there. So first off, this is performing a capability eval, where we compare the performance of the large model against those of a selection of smaller models. It's kind of like America's smallest top model or top smallest model. Oh my God, I really should have made that as a slide. I'll do that in the future. Anyway, capability eval is a way of finding out how capable is this particular workflow working. I used Claude for the baseline, which you can see in the very lowest trace here, Claude Sonnet as the baseline. I missed that. I have a laser, and I will use the laser. This is one of those situations. There we go. Here's our baseline. Look at that. We got perfect JSON. We've got perfect length compliance. We've got perfect, almost perfect accuracy. Maybe a little hallucination in there. Semantic similarity. I forget what that stands for. Anyway, well, we got this 2.9 seconds latency there, and it's clocking in around 22 cents each. Whereas all these little local models I tried, they are absolutely free, but we get some varying levels of conformance. Let's have a look at our contestants. These are the models that were tested from small to medium to large. We had Qwen 2.5 Instruct, woo, coming in at 1 gigabyte. Qwen 3, its older sister, a little more capable. Llama 3.2 Instruct, 3 billion parameters, only 2 gigabytes on disk. And Gemma, everyone loves Gemma 4. I had so many engineers be like, just use Gemma 4. Gemma 4 is amazing. Gemma 4 is kind of big. And also maybe not that amazing, as we will see. This is why you shouldn't just listen to your friends when they say, use this model. You should be like, show me the evals with my data first. I don't want to see your benchmarks. I want to see my data in my evals, your model. Friends don't recommend models to other friends without also recommending they run some dang evals. So, select the smallest capable model. Well, how do we decide which one is capable? We make a really cool chart. All that data I showed you, I looked at that, and I've looked at that, and I was like, oh my God, I have got to have that orange, I have got to have one that was totally the wrong one. At first, I thought I wanted Qwen 2.5, which is right here, because it's the fastest. Look at this 1 second latency. Look at this. Don't you want that? It's snappy. Somebody comes to your page and just boom, summaries. No wait, no spinner, just ba-bam, in your UI. That's amazing. I want that. But slow down. Its accuracy at linking to where people, like in the longer summaries, its accuracy at linking to where in the conversation someone said something was not that great. And the only way to solve for that would mean I'd have to rerun fail states, which actually would double its latency, which meant this is actually a much pudgier model, kind of more over here once you get dang. Turned out that Llama 3.2 was actually quite fast, only a little bit slower than Qwen, and it was really close to Claude Sonnet in terms of reference accuracy. Now, Gemma was super, super accurate, but it was dog slow. Look at that, 8 seconds, and we're, oh my God, Gemma, I don't know what you had for breakfast, but I mean, you're a local model. Everyone's like, local models reduce latency. No, they're small. They can be slow because they are small. They have to think harder. So you always should test them. Sometimes the remote models just are faster, even with the round trip involved. All right, so this is what those traces actually look like. And I recommend, rather than just trusting the outputs, you actually open up the traces. If you're familiar with test-driven development, traces are just another word for log. It comes from machine learning, bear with me. Anyway, it's just a log. It's just a capture of the inputs and the outputs and all that little metadata that we're tracking as well, latency. I actually popped it open, and you can see when you compare the output from Llama 3.2 with Gemma and Claude. Here's Llama, here's Gemma, here's Claude. You can see the response. You know, Sam jokingly suggests 3.1 becomes an avatar. And you know, discussing an avatar starting in this one from Gemma is actually not as good as Claude. Claude Sonnet says, oh yeah, joking about 3.1's appearance, comparing him to an avatar. Llama and Claude actually did much better at summarizing this than Gemma did. So when you actually go in and look and you make the comparison yourself, you'll see where things are lining up. So don't just trust the numbers, open it up and take a look yourself. So ultimately, the next top model was Llama 3.2. Much as it pains me to refer to a former employer who is laying off my coworkers right now, they did make one good thing. So thank you, Meta, thank you for your open source participation. You get a prize for that. To recap, here's how you do it in 4 steps. 1, prove it is possible. 2, set up success criteria. What is a fail state? What is meaning we can't ship this to production? Find a way to put a number on that. Yes, no, pass, fail. Test from small to large. Compare those inputs, the outputs of smaller models against your test criteria. And lastly, select the smallest model that gives acceptable responses for your user case. Whew. Okay, but there was still a gap there, right? It wasn't perfect. We can say that it's close, but it's not perfect. How do we squeeze better performance out of smaller models? Well, we can use this thing called prompt engineering. This is important in cases where maybe you can't control which model you are using. Or maybe you join a team and they're already committed to Gemma 3 and they are not rolling out an update until all the evals pass. Well, what are you going to do? You can still control the inputs, and that includes the prompt. The prompt is the number one thing you can control. So let's close the gap between the green circle and the blue diamond here. Let's try to get them close to one another. Whew. So these are the measurements I ultimately honed in on. Getting that JSON and reference structural validity needed to be above 99% of the times. Factual consistency, that is to make sure it's not hallucinating who said what, got to be greater than or equal to 95% pass. Needed that P50 latency to be over 1.5 seconds, and the P95 over 3.5, so we're under that 4-second drop off. So first off, isolate and optimize one step at a time. You want to test whether what you're trying, you want to make sure that you're not just throwing up a bunch of different prompts. You can do that. You can say like, hey Claude, make a bunch of different prompts, go through them all. But I found it easier to think about it step by step. I actually worked through this, got the baseline, started by trying to create numbered inputs, the same prompt reformatting the threads as numbered messages. The hypothesis is that small models can track natural language indexing better than an array of offsets. Few shot, three examples of what worked with that prompt. The idea being small models learn format from examples faster than from rules. There was this, what I call the radical negative option, which was explicitly saying no preamble, count words before responding, schno, being very, very mean to the little model. The idea being that small models like to take literal commands better than inferring what you want. And chain of thought, the hypothesis being here that if the model thinks out loud, that will improve its grounding. And I ran, there's no we here, it's just me working on this. Ran the test 3 times just to even the scores out and tested against all of them. These are how they came out. You can see that each of these prompt variants performed differently. Explicit rules was the worst. It generally tanked all of the measures, and I can't recommend using explicit rules when you're working with a tiny model like Llama 3.2. Chain of thought just slowed everything down, didn't really markedly improve things in a way that was worth the additional half a second latency. Few shot did increase the length conformance, the accuracy of the references and factualness, and didn't meaningfully overshoot our goals on latency. So yay, that was our next top prompt. Phew. And this is how they all ended up looking, the few shot ended up looking next to the bar. As you can see, we're getting really close here. We've got 91.7% structurally valid, 92.9% on the factual consistency. For the P5 latency, doing even better than Claude there. It's just nudging right up underneath 4 seconds on P95. Phew. So it turned out that the factual consistency, when I opened up the traces, because I was using Claude as the LLM as a judge, Claude was just like, this person did not think the same things were important that I did. Therefore, I'm going to be very strict and fail them. And I was like, Claude, you crazy. I'm getting ChatGPT to judge the next batch. You're being too hard on this little model. It's fine. It's fine if the model thought that Sarah had the point in this conversation and Jenny did not. Anyway, use post-processing, ref consistency and length. Those could actually be handled by the harness. I have it so that we just truncate if something's too long. That's not a make or break feature. And ref consistency can be figured out by just checking to make sure that there are no more refs than are actually existing in the conversation. And with the processing, it was able to meet the bar that I had set, and when it comes to latency, it was actually able to beat the snot out of Claude Sonnet. getting a much faster experience for people using a local model with the same level of consistency that you would expect from a much beefier model. It also saves me about $1 a day per user, which for a tiny company with no funding is a big deal. So one thing, this is not a set it and forget it situation. You don't want to lose ground. You want to update the prompt or upgrade the model in the future, or even switch to different models depending on workloads, and you'll need to keep evals for that. You'll want to have them as a part of your CI/CD. And these would be called regression evals. This is my next step, my next talk. If you come to see it in the future, at the future edition of this conference, will be about setting up regression evals in a consumer product. All right, so get moving. Let's check today. How many Claude calls could be Llama calls? Audit your current AI spending. When working on AI projects, look at small language models and specialized models. Look for local models that you can work with, like prompt, pardon me. There are local models shipping on software that you can use as well. For instance, Chrome ships with a Gemini Nano that you can use with Prompt API. Small models are more efficient. They can meet your users where they are on device. Remember to prototype big, deploy small. Prove it, define it, test it, select the smallest model that passes, and use prompt engineering to close the gap and get better results from SLMs. So if you can do one thing today, I challenge you to convert one feature to use a local model. You can find all of my socials here. If you want the slides for this, hit me up. The conference will be sharing them. Thank you.